Hi everyone, I'm Yuga from NAC Global Sales Team. I'm grateful for this opportunity to share a material of applications of high-speed camera in engine research. Today's agenda, please allow us to introduce our company profile and popular products introduction. This is roughly introduction. NAC was founded in 1958. Our headquarters is located in Tokyo, where our sales and administrative departments are based. We also operate a service center in Akasaka, which handles rental and maintenance of professional cameras and lighting equipment used in film, drama, and commercial productions. Domestically, we have two sales offices located in Nagoya and Osaka. Also, our Yokohama factory employs approximately 100 staff members and is responsible for the development of high-speed cameras, eye tracking devices, and custom-made equipment. Our sales markets include not only crash testing but also engine combustion, welding, material research, and eye tracking systems. We tailor our proposals to meet the needs of users in the research and development field. High-speed cameras are required for a wide range of applications, primarily automotive crash testing, mechanical behavior, combustion, fluid dynamics, material failure, and explosions. The required frame rate varies depending on the application. Mid-range and high-end models focus on 10,000 to 100,000 fps, meeting academic demands for combustion, fluid dynamics, material failure, and explosions. One of our key features is offering a full range of cameras from low-end to high-end models. So first, let me explain the ACS series. The ACS series is the high-end model focused on the high-speed range from 10,000 fps to 1 million fps. The ACS is capable of capturing 54,000 fps at full resolution with 1 million pixels. Additionally, this features high sensitivity with an ISO of 100,000 with model. The ACS3 is a compact model of ACS1, and smaller and lighter than ACS1. This can capture footage at 14,000 fps at full resolution of 1 million pixels. The ACS series is distinguished by its ability to deliver high resolution and high sensitivity even in high-speed imaging ranges. It incorporates a wide range of advanced imaging features including boost mode, which utilizes proprietary sensor technology to double or quadruple the recording speed and resolution. HDR functionality for only ACS3, which significantly enhances dynamic range for improved image detail in both bright and dark areas. Additionally, image trigger is possible based on brightness changes in specific areas, or download without requiring software operation. Other features include special shooting functions such as downloading a specified number of frames triggered by an input. The ACS camera's image trigger allows you to specify any detection area, subdividing the designated area into blocks of at least 21 × 16 pixels. It detects luminance changes within each block, enabling trigger detection even for minute changes in the area. This video is an observation of diesel spray. This is an example of visualization showing differences in the atomization process of fuel spray due to flow velocity. This is an observation of diesel spray combustion. This is an example of methane propane gas combustion captured by a color camera. Due to the camera's high sensitivity, the blue flame is clearly visible in the footage. This is an example of visualized combustion of hydrogen premixed gas using an RCEM, rapid compression expansion machine, provided by Professor Kuboyama of Chiba University. Hydrogen flames emit strongly at 310 nanometer and above 800 nanometer, but these are hard to observe with visible cameras. Capturing 310 nanometer requires a UV camera or image intensifier, and above 700 nanometer requires an IR camera. Monochrome CMOS sensors are sensitive up to 950 nanometer, so near-infrared emissions can be captured with a high-sensitivity camera. This video was provided by Professor Kuboyama from Chiba University. This is the result of direct imaging using the ACS3 monochrome type targeting low flame brightness conditions in lean combustion. The blue continuous band emission is extremely weak, so it's thought the wavelength of aurora was detected. ACS3 features HDR functionality. HDR utilizes sensor control technology to expand the dynamic range, enabling simultaneous capture of both bright and dark areas. This feature is effective for suppressing areas that become saturated in the image caused by high brightness phenomena such as welding or combustion. HDR function with ACS3 can simultaneously capture the same phenomenon using both long exposure and short exposure settings, then generate a high dynamic range image using both sets of data. Since the long exposure data and the short exposure data itself can also be acquired independently, it can be effectively used for observing phenomena with significant brightness changes. This video was provided by Professor Kuboyama from Chiba University. This data was captured using the ACS3's HDR function at a frame rate of 30,000 fps with an exposure time of 33 microsec and an exposure time of 1.65 microsec. This video is also provided by Professor Kuboyama from Chiba University. Data with an exposure time of 33 microsec up to -9 degrees and an exposure time of 1.65 microsec below -5 degrees are arranged in chronological order. The first abnormal combustion was confirmed with a 33 microsec exposure time, and the second abnormal combustion emission was also confirmed with a 1.65 microsec exposure time. Here are some other applications. This is a specifically processed engine borescope. Our company possesses lens processing equipment within our factory, enabling us to custom design heat-resistant and pressure-resistant borescopes according to customer requirements. The required optical materials vary depending on the observation wavelength, but we can accommodate the desired wavelength range from the ultraviolet to the infrared spectrum. This is a result of visualizing the interior of gasoline engine cylinder using a borescope. For this imaging, a separate illumination scope was used alongside the imaging borescope. This is an example of imaging the mid-infrared region using an IR high-speed camera and an IR borescope capable of visualizing the 3 to 5 micrometer range. This is an example of capturing images in the ultraviolet region using an image intensifier and a UV borescope. The left image visualizes the ultraviolet region using an image intensifier. The right image visualizes the infrared region using an IR camera. This is an example of field spray imaging using the LAS method provided by Professor Nishida. It involves simultaneous imaging with two cameras using 532 nanometer visible light and 266 nanometer ultraviolet light as light sources to analyze the spray or mixture formation process in a diesel engine. Here are the imaging results and analysis results. Visible light shows the liquid phase, UV light shows the liquid phase and gas phase as shadow images. Our company also developed analysis software. Thermias, which is our two-color method temperature analysis software, measures temperature distribution based on two-color method theory. For temperature calibration, standard light sources can be used in addition to black body furnaces. Temperature analysis results can be output as video or CSV data. This is an example of temperature analysis of actual diesel engine combustion captured using a borescope. Beyond two-color thermometry, there is also demand for simultaneous measurement of two different wavelengths. When performing that, using two monochrome cameras complicates the optical system and increases cost. Our company also manufactures a two-color split optical system capable of projecting an image onto two separate areas on a single camera sensor. The two-color split optical system is compatible with any camera and features the following characteristics. It can be connected to the camera mount, allowing adjustment of the split image area for different sensor sizes. It incorporates an alignment chart, enabling easy positioning of the left and right images. It allows filter exchange, enabling selection of any wavelength. These features make it compatible with any camera. This image was captured using a two-color splitter optical system of a hydrogen burner flame. This is an example of the results obtained from analyzing the temperature of hydrogen burner flame based on the intensity ratio of the water vapor spectrum. This is an example of temperature measurement captured using a two-color splitter optical system for TIG welding that is also used for temperature measurement during welding. Next, we would like to introduce the Alba prism. This prism optical system divides the image entering through the input window into 4 segments using an internal optical system with half mirrors and dichroic mirrors, and projects multiple images onto the same sensor surface. By attaching separate bandpass filters to the output window, simultaneous measurement of specific wavelength is possible. Furthermore, depending on the design specifications, configurations with more than 4 segments are also possible. The Alba prism features an ultra-compact design that fits between the lens and camera sensor, enabling integration into the camera's F-mount adapter. This allows switching between standard camera photography and full wavelength photography simply by swapping the mount section. Using the Gamma 10 PDX diverter device, we captured non-contact plasma experiments with a high-speed camera equipped with an Alba prism by ACS1. ACS1 is used to elucidate the reaction processes between plasma and gas by simultaneously observing the spatiotemporal distributions across 4 wavelengths. The ACS camera also features frame straddling imaging capability. Frame straddling is a technique that captures 2 sets of images at extremely short intervals. It used a double pulse laser as the light source, firing the laser pulse just before the end of exposure for one frame and immediately after the start of exposure for the next frame. This allows acquisition of 2 images at intervals shorter than the camera's capture speed. This is an example of imaging using high repetition rate double pulse laser illumination and the ACS1's frame straddling function. These capture the high-speed ejection behavior of water mixed with fine particles from a nozzle. The image on the left shows results captured at a frame rate of 25,000 fps. This frame rate is insufficient for capturing the motion of the fine particles. The image on the right shows the result of frame straddling photography at 25 Hz with a 2-frame interval of 1.3 microsec. Because the interval between frames is short, the motion of the fine particles is captured sufficiently. Finally, let me introduce the high-resolution Go 4K and 5M series. The Go 4K camera offers 4K resolution at 4608 x 2176 pixels at 1000 fps. Additionally, the Go5M camera provides high resolution of 5 megapixels with a capture speed of approximately 2000 fps. These models offer an advantage in cases requiring high resolution. This is an example of color Sri-Lan photography captured with the Go 4K. High-resolution models like the Go 4K and 5M are useful for capturing combustion and Sri-Lan phenomena. We are not only engaged in camera sales, but also provide these services special orders consulting, comprehensive support and maintenance and training for overseas distributors. These are our distributors in the world. We usually deal with numerous projects with our distributors in the world. Please contact them if you are interested in our products. Thank you for your attention.